Hi, welcome everyone. We are very happy to have you here. As Ellie, I'm Kinneret Segal, and I'm part of the engineering team in Starkware. As Ellie said, we are going to have 4 sessions today, and each session is going to start with around 15 minutes talk, and then between 30 to 45 minutes of hands-on in Python notebook. And you have the links to the talks, to the slides in your notebook. So don't worry if you don't get it right now at the talk, but you're going to have it later in the notebooks. Great. So in this part, I'm going to present the statement that we are going to prove today using the Stark protocol. And then we're going to dive in to describe the first 2 steps of the protocol. But first, we need to present some notion. It's called the Fibonacci square sequence. So what is the Fibonacci square sequence? It is very similar to the Fibonacci sequence, but we did a small twist on the sequence. So each element equals to the sum of the squares of the previous 2 elements. Okay, we did some twist in the Fibonacci sequence in order for our day to be a bit more interesting. And we represent the elements of the sequence using A0, A1, A2, and so on. Please note that this is a family of sequences, because when fixing the first 2 elements, we get a specific sequence. So for example, if we start with 1 and then 3, the next element would be 1 square plus 3 square, which is 10. The next one is 3 square plus 10 square, which is 109, and so on. We have a tiny problem, though, because it grows really, really fast. So in order to fix that, we are going to take our elements modulo some prime number. So for example, if we look at the sequence we just presented and we take it modulo 7, we get much smaller numbers, because the third element would be 10 modulo 7, which is 3, and so on. Today, throughout the entire day, we are going to fix a specific prime, which is the prime you see here. Of course, everyone here see that it's prime, right? No, I'm just joking. Trust us. We checked that, OK? But if you want, of course, you can check it by yourself as well. So this will be the prime for the entire day. And maybe some of you already noticed that doing arithmetics over a modulo some prime number gives us a finite field. So this will be the field we are going to discuss throughout the day. Great. So this was the Fibonacci square sequence. And now we are going to describe a statement using this sequence. The statement is going to be the input for our protocol, what we are going to prove today using the Stark protocol. So the statement is the following. There is a number x such that if we take our Fibonacci square sequence modulo our prime, starting with 1 and x, the 1023rd element would be this specific element. Again, I'm going to repeat it because it's crucial to understand the statement in order to understand the entire day. So we are going to prove that there is a number x such that if we compute the elements of the Fibonacci square sequence modulo our prime, starting with 1 and then x, the 1023rd element is the element you see here. 2 points I want to point out. First, it's not very important to understand. It's not important to know who x is. It is just important to know that it exists. But because you are the provers today, you do need to know x. So this is going to be the x that we will use. Okay? But for a verifier to verify the statement, it's just important to know that it exists. And secondly, of course, the Fibonacci square sequence, we could have computed it again and again to get other elements as well. But this is our choice to stop at the 1023rd element. So for today, we are computing only 1023 elements. Great. So this is the statement for the protocol. And now let's dive in to understand the first 2 steps of the protocol. So I'm going to present first the low degree extension, which is, maybe some of you know it, but if you don't, I'm going to explain everything you need to know. And then a commitment phase. So what is low degree extension? So it is a mathematical method that helps us to encode our sequence, our data, and we're going to do it in 3 steps. First, we generate some input. Then we do an interpolation, and eventually we do an extension. So again, I'm going to explain what low-degree extension is in general, and not Stark specific, and then I'm going to show how we are using it in our protocol. OK, so we have some input, y0, y1, y2, a sequence of elements. And we choose some other sequence for our own convenience. We're going to show how we are choosing it. And we view them as a set of pairs. xi goes with yi. OK, you see it on the screen, the green points in the plane. The red points in the plane. Then we interpolate a polynomial through these points. Okay? For each, we interpolate a polynomial f such that for each I, f of xi equals to yi. Okay? So to the left, you have the table, x's and then y's. And you can see the blue curve that is the result of the interpolation through this set of points. So this is the second step. And lastly, we pick a much larger evaluation domain, and we compute our polynomial f over this domain. Okay, so again, we have a set of points, the x prime points, a much larger evaluation, a much larger domain than the elements we started with. And we have the f of x primes, which are the result of computing f on these points. You see them in the green points. You see the original red points, the y's, and then you see the curve, which is the result of the interpolation. And eventually, you see the green points, which are the result of this extension. To get some intuition, we encode our sequence using a polynomial, and then we evaluate the polynomial on a much larger domain, because then if we miscalculate some of the green points, we can still understand the curve because of the redundancy. So that was a low-degree extension in general, and now let's see how we are using it in Stark. So our input would be, of course, our Fibonacci square sequence, A0, A1, A2, until A1022, And we call it the trace, because this is like the trace of the computation. Then we choose an element from our field. You're going to get the details in the notebooks, but just for now, it's important to understand that it has some different powers, okay? G squared different than g to the power of 3, and so on. And we view them as a set of pairs. G to the power of I goes with AI. Now, we interpolate a polynomial through these points, so we encode our sequence using a polynomial. So we get the polynomial f such that f of g to the power of I equals to AI. And you see the blue curve again, just as we've seen before. And the last step is choosing a larger evaluation domain. So in our case, the origin domain was of size k, and our evaluation domain will be 8k large. And it will be of the following form. We choose w and h from the field. Again, it's not really important to understand right now how we are choosing them. You're going to get the details in the notebooks. But just for you to know that this is going to be the format of our larger evaluation domain. And we compute our polynomial over this domain. Maybe some of you already noticed that this is actually Reed-Solomon encoding. If you don't know it, don't worry. But if you do, it might ring a bell. Great. So we have our large evaluation domain, and we have the evaluation of the domain. You can see it again here in the curve. So you have the original set of points, A0, A1, A2, the red points. You have the polynomial that we interpolate through these points. And you have the green point, which is the evaluation of the polynomial on the larger domain. Please note that this visualization, it is done in the real numbers, but we are doing our arithmetic over a finite field. So this is just for an intuition. Great. So this ends up the first step of the protocol, encoding our sequence using a polynomial. Now, we are ready for the commitment. We are going to commit on our data. So how are we going to do it? We are going to compute a tree that its leaves are the results of the low-degree extension, the f's that we just computed, 8k. And to create the tree, we are going to hash each of them to get the next layer of the tree, and again until we reach the root. So the leaves are the data we just calculated, and the inner nodes are hashes of the previous layer. This is called the Merkle tree. Probably some of you know it. If you didn't know it, now you know it. This is a Merkle tree. And we are going to send the hash of the root to the verifier. So we wanted to commit on our data. One option is to send the entire 8k elements. But using the Merkle tree, we just need to send one element, the root. Great. So that sums up the first two steps of the protocol. Let's summarize. So we presented the statement that we are proving today, that there is an x such that if you compute the Fibonacci square sequence modulo our prime until the 1023rd element, we get this specific element. And then we dived in to present the star protocol. The first part was encoding our sequence using low-degree extension, and then the commitment phase. In part two, we are going to understand how to generate some polynomial constraint that will help us to prove our statement. But first, now it's time for coding. So you are going to code the low-degree extension of the trace, and then to commit on the low-degree extension trace.